So let's consider the force of gravity between the sun and the earth. So we got the sun, we got the earth, and of course the earth is going around the sun. Okay. The mass of the earth, and we normally in astronomy just use a circle with an X to indicate earth. The mass of the earth turns out to be 5.972 times 10 to the 24 kilograms. Mass of the sun, and we use a circle with a dot in it to indicate sun. Okay, that turns out to be 1.989 times 10 to the 30 kilograms. The distance between the two is on average 1 AU. Okay, so that's the average distance between the Earth and the Sun, so that's going to be the radius of the orbit. Now, this is not exactly correct because the Earth's orbit's not exactly a perfect circle, but this kind of gets the idea across. We're going to pretend that it is for this problem because otherwise it's a little more complicated than we want to do at this stage. So that 1.496 times 10 to the 11 meters. And so what I want to know is what's the force of gravity between Earth and the Sun? Simple. G m1 m2 over r squared. So in that case, this would be G mass of the Earth times mass of the Sun over r squared. So the force here is going to be equal to 6.67. And then we can actually extend one more digit if we want, 6.674 times 10 to the minus 11 Newton meter squared per kilogram squared times the two masses here, mass of the Earth, 5.972 times 10 to the 24 kilograms, times the mass of the sun, 1.989 times 10 to the 30 kilograms, divided by an AU, so that's 1.496 times 10 to the 11 meters squared. So the force between the two turns out to be a whopping 3.54 times 10 to the 27 newtons. Now that's actually huge, okay, but remember Earth is huge, so Earth is actually huge too. So this this is not going to be overwhelming. It's enough to keep Earth in orbit, okay. But there are some interesting things here. That as the Earth goes around, one side is a little closer than the other. Also, just like before with tides, you're gonna have a tide here, and as it's moving, get a tide on the other side. There's actually solar tides. Even if the Earth had no moon, you would still have tides because of the gravitational interaction between the sun and the Earth. So you're still going to have tides. The moon's tides actually are on top of that. So that means when the moon is lined up here or there, so either new moon or full moon, you get extra big tides. And when the moon is at first quarter or last quarter, you get extra. You have the lunar tides and the solar tides. So the lunar high tide occurs at the solar low tide, and they tend to cancel each other a little bit. The moon's tides are bigger because it's actually closer to us, but what happens is you get wimpy high tides and wimpy low tides, and so the size of the tides depends quite heavily on the orientation of the moon relative to the sun. Well, let's get back over here. We know that the gravitational force is what's keeping the moon or keeping the Earth in orbit around the sun. So that is providing the centripetal force. So the gravitational force is the centripetal force. Well, that means that the G mass of the Earth times mass of the sun over r squared is equal to mass of the Earth v squared over r. Well, that means that we can solve for the speed the Earth goes around the sun. That's going to be equal to square root of g times mass of the sun divided by r. So if you plug in our numbers, because we know what these numbers are, so we have 6.674 times 10 to the minus 11 Newton meters squared per kilogram squared times the mass of the sun, 1.989 times 10 to the 30 kilograms. Then you divide by r, which is the 1.496 times 10 to the 24 kilograms. And what you find is that the orbital speed here is 29,780 meters per second, or in other words, 29.78 kilometers per second. So that would be if Earth were actually going in a perfectly circular orbit. It's not a perfectly circular orbit, but it actually does come pretty close. Okay, so that would be the orbital speed. That's how fast Earth is moving as it goes around the sun. And so in terms of astrodynamics, when you talk about interplanetary travel, you have to figure out how fast is one planet moving, how fast is the other planet moving, because if you send a spacecraft from one planet to the other, you got to have an orbit that transits between two different sort of things, and you got to be careful because these are pretty high velocities out here. You don't want to just send a spacecraft to another planet and then have it be going the wrong speed when it gets there, and then you can't actually catch up to the planet, or the planet runs away from you, or the planet slams into you or something. Okay. So, well, the next question is, how long would it take to go around? Well, we know the orbital period is going to be the distance around, so there's the sun, divided by the velocity. Well, that's going to be 2 pi times the distance around, which is 1 AU, 1.496 times 10 to the 11 meters, divided by, we'd said this was 29,780 meters per second. So the orbital period comes out to be 3.156 times 10 to the 7 seconds. Well, we know that 1 day is 86,400 seconds. So if I divide there, this comes out to be 365.3 days. Okay. And so, well, how long does it actually take to go around the sun? Okay. And that actually takes 365.26 days for one, what we call sidereal orbit. So that's the actual orbital period that it takes to go around the sun. Now, of course, it turns out as Earth goes around the sun, it also changes the tilt slightly. So the seasons repeat every 365.24 days. Okay, so that's what we call a tropical year. That's the seasonal year. And then this is a sidereal year. Okay, and of course, a calendar year is going to be pretty close to in between there, 365.25, except we actually skip a leap year, 3 leap years every 400 years. People don't really realize that's one of the rules. And so that brings the actual calendar year over 400 years closer to 365.24, which is why the calendar keeps track of the seasons real well.